This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, professor for this class, and this is Lecture 23, the second half of our two-part lecture series on sputtering, sputter deposition. Our reading is to finish Chapter 12 of our textbook by Campbell. Step coverage. We've seen and talked about step coverage a couple of times now. What is important about step coverage with respect to sputter deposition? Well, step coverage is pretty good. We can create pretty good step coverage. Not perfect, you can never make it perfect, but you can make it pretty good by having a small mean free path, which means lots of scattering of the material that's being deposited. It reaches the wafer coming at a large range of angles, and the result is good coverage of the steps. Shadowing still occurs, it's just not as significant because there's a range of angles. Line of sight types of deposition systems like evaporation have much more significant shadowing effects, but you still get some shadowing with sputtering. We can improve step coverage by trying to improve the mobility of the deposited material after it hits the wafer. So we have actually two different phenomena. One is sticking and the other is diffusion. Sticking means, does it stay where it first lands, or does it sometimes bounce? If it bounces off, it can actually land somewhere different. But we're not going to talk that much about sticking and the sticking coefficient. But even if you have material that sticks where it lands, you can still increase the mobility after sticking. That's a simple diffusion process. If you heat up the wafer, the materials can diffuse around, move around. But there are problems if we get too hot with metal. Metal grains can form. That is, metal is not a perfect crystal as it's being deposited. It's not completely amorphous either. We get grains of single crystal material, and these grains can form, and the boundary between the grains can have some problems associated with it. Reliability problems, conductivity problems, and the material can become rough because of these grains. We use the specular reflectivity to monitor how rough the film is. The specular reflectivity is the reflectivity that obeys the law of reflection. The billiard ball, whatever angle the light hits, it reflects off at the same angle. The normal mirror reflection. You can also get scattering. This is diffuse reflectivity, the non-specular reflectivity. That's scattering off of roughness. So you can measure both, but it's actually a lot easier to measure the specular reflectivity, the straight, bouncing off the surface like a billiard ball would. And if the specular reflectivity starts to go down, that means the scattering is going up. If the scattering goes up, that's an indication of roughness. So a very easy way of monitoring whether our metal grains are getting too big, whether we're getting too much roughness in the surface because we've heated up our wafer a little bit too much to try to improve our step coverage, is by monitoring the specular reflectivity. If it goes below some spec limit, some specification limit, maybe it's 80%. If the reflectivity drops below 80%, we might say we have a problem. We need to fix it. Now, there are some applications, though, where good step coverage isn't necessarily a good thing. Let's look at something called the via fill application. So here I'm showing a contact hole. So think of the blue here as oxide and oxide. Here's the wafer, and I've made a hole, a small hole. I show a cross section of it, but you can think of a circular hole through the oxide, and I want to make a contact, so a metal layer that will come in and contact this. I'm going to do that in two steps. First, I'm going to fill up this via, this opening, this hole, with metal, and then I'll lay a metal line on top of it to make a contact with the top of the via fill. So I've got this via, I need to fill it up with metal. What do? Well, I start depositing. Suppose I start depositing with a standard metallization process with sputtering. I get some reasonable, not perfect step coverage, but because of shadowing, the right here in the corners, I have the least thickness of material. Even though I get target atoms coming at a wide range of angles, right? Still, there's a limited, because of this 90 degrees here, a limit to the range of angles that can make it into the corner. As I grow that film thicker and thicker, eventually the two tops here and here might touch each other before I've filled up the material in the middle. The result is called a void. And these voids can pose very serious reliability problems. Eventually what I want to do is planarize. I want to come down with a polishing pad and polish off all this top stuff so that the only thing I have left is this filled up via, filled up with the metal. But this void can cause some damage, some defects in this fill, and in fact the void might survive. It might actually stay in the via fill and cause a reliability problem. How can we avoid this? Well, we can avoid this by having worse step coverage. All right? I'll talk about how we create worse step coverage. First, let's look at what the effects might be. There's our fill that we want to fill up without a void. We start filling up, but this time we'll use a process with poor step coverage. So you see the thickness on the sidewalls is less than the thickness at the top and the bottom of this feature. Because of that, we grow the thickness. It goes faster vertically than it does horizontally. And when we're done, we've got a place where there's an indentation, yes, but there's no void that is inside of this material, and certainly it's not inside the via. Now I do some CMP, chemical mechanical polishing, a process step that we're going to talk more about in later lectures, and I polish off the top. So all this material on the top gets polished off until I reach the bottom. I'm left with a smooth surface where the via is completely filled and all the rest of the metal is gone. That's what I'm striving for, and I'm able to achieve that by using a deposition process with poor step coverage rather than a deposition process with good step coverage. So it really does depend on your application whether you want good or bad step coverage. It would be nice if we could control it, if we can adjust the amount of step coverage. And we can do that. How do we reduce step coverage? Well, we need to have low step coverage. We need the direction that the target atoms hit the wafer to be nearly vertical. Well, you think I'll just lower the pressure so that my mean free path now becomes large compared to the distance from the target to the wafer. But that distance is in the tens of centimeters, close 100 up to 100 centimeters. Now, usually not that much, but tens of centimeters. And that means I have to have a fairly low pressure, which means I have a low number of argon atoms, which means I have a low number of argon ions, which means I have a low sputtering rate, which means I have a low deposition rate. So just using pressure to increase the mean free path and make the ion direction more normal is a difficult thing to do. The result is very, very low deposition rates. We don't like that. What else can we do? Well, this will reduce the deposition rate a little bit, but not as much. We're going to reduce the pressure to a few millitorrs so that the mean free path is on the order of a centimeter, but not on the order of tens of centimeters. So we can have an order of magnitude or 2 orders of magnitude higher pressure than we would have to otherwise, which results in higher deposition rates. But we're going to use something called a collimator to direct the sputtered atoms vertically, because 1 centimeter is still small compared to the distance from the target to the wafer. But we'll put this screen above the wafer. And the screen has some openings in it that are tall enough such that any random target atom moving in a random direction that goes into this will not be able to make it through unless it's going fairly vertically. And so if it's going fairly vertically, it can make it through this screen. And if the thickness of the screen and the distance to the wafer is less than a centimeter, and the mean-free path is a centimeter, once a target atom makes it into the screen, it's unlikely to have a collision. So it will keep going in the direction that it started with, which means all of the target atoms coming out the bottom are going nearly vertically. Of course, we've got these regions underneath the screen where there's no target atoms coming. So the only way to get a uniform film is if I scan this wafer back and forth underneath the screen, and in that way create a more uniform film thickness as it's being deposited. This slows down the deposition rate a little bit, but not as much as if I really reduce the pressure. And it frankly produces better results given the size of the target. Another approach is to ionize the sputtered vapor and then direct it with an electric field. We know that if we ionize an atom, we can apply a direct electric field and get it moving in the direction we want it to go. So it is possible, instead of using neutral target atoms, to create a plasma of those target atoms after the sputtering has occurred and use an electric field to direct them down to the wafer. So that's the second approach that we could use to reduce step coverage. Another interesting thing you can do with sputtering that you can't do with evaporation is something called sputter cleaning. Here's the idea here. We're going to start with our normal sputtering system, but now we'll make the wafer have a slight negative bias compared to the plasma. So there's a voltage difference between the plasma and the target, which is quite large, and so the argon ions will hit the target and create the sputtered vapor of the metal or other material that we're trying to deposit. But we can also make the wafer have a negative bias compared to the plasma. So some of that argon ions will sputter in the wafer too. So if you've got some little gunk, some dirt, some residual material from a previous process step on the wafer, you can clean it off in situ. Before you start depositing new materials, it will start etching, these argon ions will start etching the wafer. Sometimes you might have a native oxide on the silicon. Silicon, by the way, if you just leave it in the atmosphere, will grow a few angstroms, up to 10 angstroms typically, of oxide without doing anything, just in a normal room temperature atmosphere. It's called the native oxide. It's very thin, 1 nanometer thick, but it can still be a problem, especially if what you're trying to do is create a good metal contact to the wafer, to say a source or a drain. So we can remove this native oxide with just a little bit of sputter cleaning to begin our deposition process. Now, a problem is this sputtering might actually damage the substrate, especially if you have some part of the substrate that's quite delicate, that you don't want any kind of sputter etching of it before you deposit your material. So you weigh that against the value of sputter cleaning. Related to sputter cleaning is something called bias sputtering. So we might turn on that bias at the very beginning to get a little sputter cleaning and then turn it off once the main deposition begins. But we can leave that bias on during the deposition as well if we'd like to. What will happen if I'm depositing material and at the same time I have a little bit of etching going on? Now I have to assume, if I want any deposition to occur at all, that the rate of deposition exceeds the rate of etching. But in a sputter system, the direction of deposition is more uniform, depositing from all angles. But the etching is one directional. If I have a bias, a negative voltage on the wafer, and I put in some positive argon ions, the electric field will direct the argon ions straight down. These ions won't be going in lots of directions. Of course, they can still scatter, but even if they scatter, the electric field will start pushing them straight down again. So I could possibly get some sputter etching of the metal on the wafer as I'm depositing it. I'm presuming that my deposition rate will be faster than my etch rate, but nonetheless, that etching will result in some sputtering of this material. Now, it'll sputter off the top as well, but we don't really care about that. That just changes the deposition rate. It won't really sputter off the sidewalls, but it will sputter off at the bottom. And where are those sputtered metal atoms going to go? Chances are they're going to redeposit on the sidewall. I'm etching down into a hole here, or I'm etching into a hole with a little bit of metal at the bottom, and so often these etched metal atoms, the sputtered atoms, won't make it out the hole. They'll actually hit and redeposit on the sidewall. The result is better step coverage and also a more uniform thickness of material at the bottom of this hole. So let's talk about an example process. One of the common processes for depositing a metal is aluminum. Aluminum was the dominant metallization technology through the 70s and 80s and most of the 90s. Since then, we've replaced aluminum with copper in our high-end parts, but aluminum is still used in older parts nonetheless. And when we deposit aluminum, we actually deposit an alloy. It's mostly aluminum, but with about 2% silicon and about 0.5% copper. That results in a metal that has some better electrical properties and better reliability properties in particular. So how do we deposit an alloy with the sputtering process? Well, it's very easy. Essentially, the rate of the sputtering of aluminum or silicon or copper is about the same. So we can simply make a target that has the exact composition for the material that we want to deposit. And we'll pretty much get the same alloy composition for the deposited material as the original target. We'll use a planar DC magnetron sputter deposition system. Planar means the top and the bottom electrodes are planes parallel to each other. We use the DC magnetron, so a DC electric field and a magnetic field to get the electrons to spiral through the gas to create the plasma that results in a high density plasma and a high deposition rate. It's important that we keep contaminants like oxygen and nitrogen in the chamber very low to prevent any chemical reactions with the aluminum. Another important factor in the deposited films is stress. Stress in metal films can affect their reliability when we're using this. If we run current through a film that has stress in it, the grain boundaries in the metal can start moving around. And this motion can be accelerated by the use of current, and so we can get reliability failures in the metal lines as current runs through them. They can break. So this is a problem when we try to deposit films with low levels of stress. Where does the stress come from? One common way to get stress in a film is to deposit it at a high temperature and then have a mismatch between the thermal properties, the coefficient of thermal expansion of the metal compared to the substrate. So I get deposition at one temperature, but when they cool off, maybe the metal shrinks more than the silicon does, and the result is stress. Stress is measured as a change in the wafer bow, both before and after deposition. To finish up our discussion about both evaporation and sputtering, and in fact when we start talking about CVD deposition of materials as well, I'd like to go through some of the things we've already talked about concerning the quality of the film that we're depositing. plus bring up a few other topics as well. There are a lot of factors that go into being able to describe a film as being high quality. A lot of factors that determine how useful that material is for its intended purpose. First of all, maybe the most obvious thing is the composition. We're trying to achieve a film with a specific composition that has low numbers of impurities, has the right stoichiometry if it's a molecule, or the right composition if it's an alloy. We want it to have the right electrical properties and mechanical properties. We just talked about stress as a mechanical property of the film, but we also have electrical properties. Things like the resistivity for a metal film. The breakdown voltage for a dielectric, that is, what voltage would it take for that dielectric to start acting like a conductor? You hit high enough voltage, the dielectric breaks down. Think of a spark breaking through the insulator if the voltage gets too large. That's called the breakdown voltage, and we want that to be particularly high to have good electrical insulating characteristics with good reliability. Defects: we want a film that doesn't have any pinholes, that doesn't incorporate any particles. We want good adhesion of the film to the substrate that we're depositing upon. We want the right thickness, that is, hitting the right thickness, that's the accuracy of the thickness, and then good uniformity. Uniformity across the wafer, wafer to wafer, lot to lot. We want the right step coverage. Maybe we want good step coverage, maybe we want poor step coverage. We want the step coverage we want. We can look at the extremes of a planarizing film or a conformal film. Conformal film is what we think of as perfect step coverage. The thickness on the sides of our sidewall are the same as the thickness at the top. We call that a conformal coating. Or a planarizing layer where, think of water covering a surface where the top surface is a plane regardless of what the topography is underneath. And finally, as we mentioned, reflectivity is used to describe the roughness of the surfaces, but also, especially for dielectrics, the refractive index of the material, which is an optical property of the material, can be very important for subsequent process steps, in particular lithography, which we'll talk about later in the class. Well, that's lecture 23. What have we learned? You should be able to quickly and easily answer these questions. If not, you might need to go back and review some of the material in this lecture. How is step coverage controlled in sputter deposition systems? What step coverage is needed for the via fill application and why? What causes stress in deposited films and how is it measured? And finally, how many aspects of film quality can you name? Hopefully all of them, but hopefully not just a couple. We've looked at a lot. Well, that is our second and final lecture on sputtering and the last of 4 lectures on the topic of physical vapor deposition. Next time, we'll begin discussing chemical vapor deposition. Till then.